So, Vanakkam. So, we will continue our lecture on engineering seismology. So, we have been discussing about the microzonation hazard index estimation. So, we have seen that in any area, okay, depends upon the exposure, okay, what are the different possible hazard is expected. So, we can list out all those hazard, okay, systematically, which is called as a earthquake hazard parameters. Okay. So, depends upon the city, it keep varying. As we told that the coastal city, tsunami will be the part, the hilly terrain landslide will be the part, and then the middle of the any regions like this Delhi or the Bangalore kind of things, both are not possible, but the other hazard may be possible. So, irrespective of the place, the earthquake hazard at the bedrock level is a common attributes, okay, common seismological attributes, okay, which will be necessarily counted in the seismic microzonation as a first and foremost step, which is that seismic hazard due to the nearby seismic sources up to bedrock level. Okay. Then depends upon the soil thickness and stiffness, okay, the waves are going to get modified. So, you can add a geomorphological attributes which reflect a topographical, soil thickness, soil type, okay, these are all the geomorphological attributes, and then again estimate how much amplification going to take place. Okay, that is the again seismological attributes where you consider earthquake as a input to estimate a amplification. Then the liquefaction depends upon the cohesionless soil, cohesionless soil undergo a liquefaction and cause extensive damage. So, we have to count that as a one of the seismological attribute in the regions, okay, where the cohesionless soils are predominantly present. So, then obviously the cohesion liquefaction is done, landslide, okay, tsunami. So, you can list all of them and rank and give the weights. So, you assign a weight based on the decision maker past history of the earthquake. So, you can assign the more weightage and less weightage depends upon the importance of the each parameters. Okay. Once you assign a weight within the parameter, we have seen that there is a division. Okay. For example, one region, Bangalore region, the soil thickness may vary 0 to 40 meter. So, I should give more weightage to the 40 meter soil and less weightage to the 0, because the more and more soil, there is a more and more amplification and liquefaction and wave modification. So, that has to be ranked, okay. So, which is to be given a higher ranking, then estimate a normalized rank. Once you estimate a normalized rank, you already estimated the normalized weight based on the each earthquake hazard parameters. Then you multiply each grade the normalized rank and the weights, and then for each parameters finally make add all of them and estimate a final hazard index value. This hazard index value varies from 0 to basically 0 to unity. It will varies from 0 to unity. So, the 0 and highest value will be the unity. So, the I1 will be the highest hazard. Okay. So, here we should remember that this value 1 indicate a more severe, but again this will vary depends upon the weights what you assign for each parameter. Okay. So, that means it is not uniformly same for all the region. So, one place you get a hazard index value of 0.5, the other place you also get a 0.5, the 0.5 both are not indicating the level severity. One place this may be the low, another place this may be the very high, okay, because of you assign a weight, okay, yourself decision maker assigns a weight and then estimate a pairwise matrix of the normalized ways, which is depends upon the user. Okay. So, you can estimate this by the deterministic approach and probabilistic approach. So, let us see how this typical study was done for the Bangalore city. As I told you that it was done part of my PhD, and where we consider all the possible scenarios and finally arrived a hazard index map of the Bangalore. We discuss how this hazard index map for the deterministic and probabilistic based approach results are varies. So, right now I am not going to discuss each hazard parameter estimation in detail, only I will give you the glimpse. Okay. So, because that itself is a separate topic of research. Okay. So, it can be taught as a separate course. So, right now I am not doing that. So, the first foremost step I told you that estimate a bedrock level hazard. So, this particular step we are going to discuss part of our course. Okay, after finishing the couple of lectures, we will be going to do seismic hazard analysis of the any particular place with the case studies. So, this is the seismic hazard analysis has been adopted, and then we mapped a PGA distribution of the each city. Okay. So, each grid we mapped a PGA distribution. So, the PGA distribution has been mapped, and you can see the distribution of PGA, which is varies from lowest value is basically 0.1. You can see this is a 0.1 is the lowest value, the highest value will be the 1.5. So, this has been divided as how many grid? Totally 5. So, the 1, 2, okay. So, then the 1, 2. So, the yellow one is actually this one. Here also this is the 1 actually, this is the 2. So, this is the yellow one is a 3. Okay, this is the 3 basically. Okay, so, once you are done the 3, this is actually the 4. So, the dark red one will be the 5. Okay. You can see that the hazard was actually 5 category distributed here. So, okay, the 4 categories are this area wherever you can see. So, this is the and this part is the 4. Okay. So, this is how the hazards are distributed. Each grid is one value depends upon the earthquake magnitude, distance, and then nearby active source. So, all those things taken into account, finally it produced for the Bangalore by systematic approach. So, which we will be discussing in the later stage of the our class. Once you are done that, as I told you that the next affecting parameter is here your soil. Okay. So, what we discussed earlier was actually the deterministic based approach. So, same way you can estimate a hazard for the probabilistic based approach. So, this method also we will discuss end of our course. So, where we will be talking about how to estimate a probabilistic based hazard at each grid. So, here also you can see a different zone 1, so 2, 3, okay. So, the 4 and 5. Okay. So, maybe I should use some other color. Okay. So, the 1, so 2, so 3 also visible. So, this is the 4 and this is the 5 you can see. So, this is the 4, 5. So, 5 group. Now, you can see the change in the hazard pattern. You can see here the deterministic hazard actually the hazard was highest on this part, which varies like this. Okay. It is low here, high here. But when you talk about the probabilistic, basically it varies like this. Okay. So, this side is a low and this side is a high. Okay. So, this is because of the procedural difference and then uncertainty associated with that, which we will be discussing in detail in our class in the later stage. So, this is about the hazard at bedrock level. So, right now we are ready with our map at bedrock level. Okay. Bedrock level we mapped. As I told you that the other important parameters which contribute the modification of the hazard is the soil parameter. So, the mapping of soil average, okay, has to be considered. So, for this we have done a detailed geophysical geotechnical investigation and collected a data and tried to arrive a Vs value, shear wave velocity, which is basically shear modulus, okay, because the G is equal to rho into Vs square. So, the rho values are variation small. So, the Vs square can be considered as a your useful hazard, okay. So, indication at a particular location. So, with that point the Vs has been measured the entire area of this one and mapped that. So, since this is not part of our scope, I am only talking about the map, how the map has come. Okay. So, we mapped a Vs distribution based on the Vs 30 average. So, if you want to know about the Vs 30 average, Vs measurement and all, you can refer some of my publication and Google for the more information. So, you can see the distribution, there are 3 category you can see. So, one is that site class D, which is like more dangerous, then the C, which is relatively less dangerous than the D, and then the B, which is again relatively. So, this is basically a lal bog. This area is lal bog where you can see a outcrop. So, where you can see IAC and all, as I told you that here the shallow bed rocks, the rocks are also outcrop. You can see it is comes under the category of the D and then the C. Okay, these are all the major area comes under the category C. So, like that you can divide this 3 category which is based on the equivalent soil shear wave velocity. So then you can also estimate a thickness of the soil. Okay, so again you can see the thickness of the soil map from the bore log. You can again see the higher thickness and lower thickness. Okay, so depends on that you can assign a weightage factor. You can see the thickness distribution. Okay, you can rank them. So this is the data based. For this, preparing both the map, you need a geotechnical and geophysical investigation data. Okay, basically you need to get a geotechnical and geophysical investigation data. So this data basically as close as you represent, the accuracy of the mapping grid will be increased. Okay, so generally there is a 500 by 500 grid size for the more variation based sites, and then 2 km by 2 km grid size for the less variation sites. So, okay, with respect to topography and soil variation, that is how you can do and prepare this kind of map. So, once you are done that, so next level is to estimate how much amplification going to take place by considering all the previous input. Okay, the hazard values and soil data clubbed together and modeled how much amplification going to take place, and then map a amplification distribution map. So, you can see that the rocky regions where your amplifications are negligible. Okay, the more soil region you have, the more amplification values. Okay, so this is what you can see in the map. So, which is the function of earthquake as well as the soil, not only soil alone, but some indication. So, how much PGI is taken, okay, how many layers systems are there, what is the density and VS variation, all those things contribute this. So, this map has to be estimated systematically. So, this kind of research I do, but I am not teaching part of this course in detail, because the site response analysis itself can be taken as a 5 to 10 hour class, depends upon the in-depth knowledge what you want to go. Here we are not discussing that, because our objective is only to introduce engineering seismology to you. So, not going into this one, because this is all done with a lot of extensive field and numerical analysis of the data. So, once you are done that, so you can also measure a predominant frequency or the resonant frequency of the area by experimental way, which is experimental site response analysis or experimental site response studies. So, where they will deploy a micro tremor instrument, which is like seismometer, and monitor a vibration noise, and then take H/V ratio that gives the predominant frequency of the soil column. So, for example, in one location you deploy a equipment, okay, you measure a predominant frequency of say 4 Hz, okay, so which indicates that the natural frequency of the soil column in this is actually 4 Hz. When you want to build a building, okay, you should see that which never matches with the natural frequency of the soil column. You should be away from the natural frequency. So, that what will help you. So, that kind of data will be obtained by carrying out a micro tremor studies, which is called as a Nakamura method, micro tremor studies. Such extensive study I used to do, because as I told you that we have a seismometer with us, okay, where we deploy a seismometer and measure a micro tremor signals, okay, then estimate a H/V ratio. So, recently we are doing this kind of extensive study for Coimbatore, Bangalore and Bhubaneswar. So, where we have done almost close to 600 points, okay. So, in the Bangalore, around 550 points in Coimbatore, around 1500 points in the Bhubaneswar, because the Bhubaneswar is a big city. So, where it has been systematically this equipment has been deployed and noise has been measured and predominant frequency has been estimated. So, even I do have published a paper on how the predominant frequency of the region varies, how it is related to the thickness of the soil column. So, which we have done for the Indo-Gangetic basin, which is the first time unique work in India, where we related a thickness of the soil column from the bore log data available from Indo-Gangetic basin with the predominant frequency. If you want more information about this, you can visit my publication pages and you can get more information there. As I told you that each component of microzonation is a separate topic of research. Okay, so, we do research on that. We try to establish and estimate parameters and say that how you can estimate more representative way. Okay, that is what we publish. So, but here since it's introduction class, so on engineering seismology I only say how it has been done orally, I am not discussing in detail. So, in case if I offer alternate course in the future where I will be talking about all these things in detail in that course. Okay. So, we estimated the amplification and predominant frequency which is responsible for building damage due to the wave modification. Okay. So, that is what we have taken. So, once you have done that, the next, as I told you, that the cohesionless soil where the liquefaction is possible. So, the liquefaction generally happens in the cohesionless soil, okay, not on the cohesive soil. So, the cohesionless soil generally found by the fillings. So, generally this Bangalore, I do not know how many of you know the history of the Bangalore. So, the Bangalore was once had a 73 lakes. Okay, if you go back to the history time about 100-200 years back, the Bangalore is actually having a plenty of lakes. Okay, old lakes are there. These lakes are actually stored for the water for drinking and agriculture purpose those days. But due to the agglomeration of the people who migrate from the different part of this one to the Bangalore city, the Bangalore became a city. So, then the Bangalore lakes has been filled officially and unofficially by the people, even by the government, and then they made a residential layout. When they are filling generally, you can expect that the filling will be done generally excavated materials from somewhere or a demolished material. So, this kind of filling actually as the available material they use. So, these fillings, loose fillings may cause the more dangerous phenomena called liquefaction and settlement. So, this area what I told you that we collected systematically geotechnical and geophysical data and try to estimate that, and then considering the hazard value amplified from the previous step and estimated the liquefaction of the Bangalore city. So, even though the Bangalore is not highly liquefiable, but still for the procedural wise we are given a step by step method. If you go to my microzonation paper or the liquefaction analysis of Bangalore, you can see how we have done a systematically liquefaction analysis considering the state of art knowledge as on today. Okay. So, whenever that map was done that time. So, we have done that and estimated a factor of safety. You can see that most of the Bangalore has a factor of safety more than 2, which indicates that this is not liquefiable. Okay. So, majority which is not liquefiable except few places where the factor of safety is. This is actually some of the valley region where filled up soils are there. So, remaining place there is not much, this one was there. So, this is how you can estimate a factor of safety. As I told you that doing liquefaction analysis itself a master thesis work or PhD work. Okay. So, as I told you that here only we are talking about the map integration. I am not going in detail about the liquefaction analysis. If you want to know more about liquefaction analysis, refer my papers or any literature in the Google, or even you can approach me or my TA, they will help you to clarify some of these doubts if you are doing some PhD or MSc related to this topic. Okay. So, that is what you can do. So, we created a factor of safety against liquefaction map. So, now you can see that we basically created a different level of maps starting from bedrock level hazard, which we have discussed the deterministic, probabilistic, then followed by we created a shear wave velocity map, thickness of the soil map, and amplification map, and predominant frequency map, and liquefaction map. Since the Bangalore is located on the flat terrain region, not too much hills are there. So, the landslide is not done and it is far away from the coast. Okay, there is no tsunami has been done. So, now we estimated all the required earthquake hazard parameter as per the microzonation procedures. Okay, now we set. So, you can see all these parameters. We estimated basically 6 parameters. Okay. One is that the soil thickness using the bore log, equivalent shear wave velocity which we have seen, factor of safety against liquefaction, rock level PGA, and then the, so by deterministic approach, rock level PGA by the probabilistic approach, and the amplification factor, okay, then the fundamental frequency. Okay, so this is how. So, now I shuffled this parameter and I assigned a weight. Soil thickness is a major role as the Bangalore has a undulating terrain. So, the soil thickness at one place will be more, one place will be less. Because of that, you will get a large impedance contrast related amplification. So, I given the highest weightage which reflect a soil thickness. Okay. Then the soil stiffness which is assigned as a 4, because the amplification is the function of thickness and stiffness as per wave propagation. So, this has been assigned. So, then the factor of safety liquefaction assigned as a 4, then the PGA, okay, the rock level PGA, and which may be deterministic or probabilistic, does not matter. So, I assigned a equal weightage, because when we are preparing a map, this will be, you will be using as these two as a independent parameters separately. Then the amplification factor and fundamental period. So, I have assigned a weight. So, this weight, okay, this is the description of the whatever short form we are given in this place. So, this weight basically used to arrive a pairwise matrix comparison of their normalized weight. You can see the normalized weight, what I told you that. So, you get a normalized weight, the sum of them will be the unity. Okay. So, this is a pairwise comparison matrix where you can get a normalized weight using this pairwise comparison matrix concept. Okay. So, now you can see that the weightage factor, how it varies with this one. As I told you that each earthquake hazard, okay, parameters has its own classification, and you have to assign a rank based on the each classification. So, the soil thickness, as we have seen that the thickness varies from 0 to 20 meter and above. So, I group them as a 5 category. So, you can see the category 1, 2, 3, 4, 5. So, I assign a highest rank for the more dangerous category. So, the more thickness, the more will be the problem. So, I put that as a 5, then accordingly I will reduce the lowest category rank will be the 1. So, this is the weights which we have discussed in the previous slide. So, now I calculated a normalized rank using this, you can see. So, that means whenever the lowest is there, this weight will be multiplied by this, okay, like that. So, similarly site class 3 category. So, the site class D, as I told you that the more dangerous than the site class C and B. So, the highest rank has been assigned for this. Okay. Then the next rank, then you get a normalized ranking. Similarly, factor of safety, the liquefaction 1 is more, less than 1 is more dangerous. So, you can assign a highest weight, then the rank, then the next rank and next rank, and then this is the normalized ranking of the same. So, you can get the normalized ranking of the same. So, then the PGA distribution. Okay. So, the PGA distribution 5 group, again the 5 category, and then normalized ranking. Similarly, the amplification factor. So, the 4 group and then the normalized ranking of this one. So, similarly, the predominant frequency, okay, so where the 5 group, so the lowest frequency will be the highest dangerous for the high story buildings. So, that is why these are, so you can see the normalized ranks. So, similarly, this is the probabilistic based PGA, this one. So, these two will be taken separately when you prepare a different map. Okay. So, one at a time you can take any one of them, deterministic or probabilistic. So, you estimated the normalized weight of the each factor by the eigenvector analysis, pairwise comparison of matrix, and then you estimated assigned a rank and estimated a normalized rank. So, with this we are ready with the preparing the map. As we have seen that the hazard index, okay, at any particular place, hazard index which may be deterministic microzonation map, deterministic microzonation map. So, the each grid point, okay, I will be estimating the deterministic hazard map and the probabilistic seismic microzonation map hazard index value. Okay. So, this value is basically weights and rank of the each earthquake hazard parameter, that is what we have seen. Okay. So, if you want to, you can recall the formula what we have done. So, this is the formula what I was describing. Okay. So, this is the formula what we are describing. So, you can multiply both of them and each parameter and then sum up all of them and then indicate a values how it is done. So, like this all the maps, okay, are spatially, this you can code this formula in the ArcGIS by giving graphical input, and then ArcGIS take data from each grid point and estimate the formula values as per that, and then it produce a map like this. You can define a division. So, the disseminating hazard index values has been categorized here. You can see 0.3 to 0.7, 0.5 to 0.7, 0.3 to 0.5. So, you can see that the highest hazard has been expected on these places, because we have given basically the thickness and the liquefaction, all those things you can see the lowest. So, overall the only the this part of the Bangalore where you can expect a more hazard index value than this part of Bangalore. Okay. So, this is the findings from the this map. Okay. So, this is the deterministic seismic hazard microzonation map of Bangalore, which we have published. Okay. These publications are available in the website. So, as I told you that you can download and you can use it. Okay. So, once we have done the deterministic hazard analysis, in order to understand how the probabilistic hazard index values also varies in the region, we done a repeated a same procedure, only taken a PGA distribution at the bedrock level based on the probabilistic hazard analysis, and again produce a probabilistic hazard index value map of the region. So, this is the basically a map which shows a probabilistic approach here, deterministic approach here with a similar kind of coding pattern, okay, color coding pattern. You can see here the pattern of hazard distributions are completely changed when you go for the deterministic and probabilistic. This is basically a 10% probability in the 50 years, okay, so interval. So, that is the map what we produce. So, this you can do whatever probability you want and then whatever return period you want. This was basically a 475 years return period hazard values. Okay. So, you can see that the hazard index value also considerably different for both the method. Okay. But this is the worst case. So, when you go for the worst case, this is what you will get. So, when you go for the probabilistic approach, this is what you will get. Okay. So, this kind of difference you can try to understand. Mostly the lower probability, okay, 2% probability of exceedance in the 50 years will be equal to the DSHA results of hazard. Okay. So, similar kind of pattern you can also expect, but the composition what you, how you are making a rank and weight, okay, also matters to decide what is the hazard index value at a particular grid. Okay. So, this value, okay, this kind of map will be more representative and required for the city planning and the city development. Okay. So, the global scale map or country scale map does not account a regional soil variation which is responsible for amplification and liquefaction and modification of the seismic wave. So, because of that, the regional variation of the soil has to be modeled and accounted in the seismic zonation map. Accounting of that kind of zonation map is called as a seismic microzonation maps. So, we have seen the case study of Bangalore, how this was systematically analyzed and produced a this kind of map. So, these maps are basically they use, but only we have restricted our study only to the BBMP area during the 2004. Okay, now the city area actually extended. Okay, so this study has to be updated according to the US and world level recommendation. So, any microzonation map has to be updated frequently every 5 years or 4 years gap or soon after the major earthquake. Since there is no major earthquake, but it was done on 2004, now we are in 2020. It is almost okay. So, 2007 we published officially, it is okay. So, even 2007 if you take, it almost 13 years are completing by preparing this map. Okay. So, now it is a time for updating this kind of map. So, we have shown this basically to demonstrate how the hazard parameters are varies how you can precisely estimate using the state of art knowledge developed in the world. Okay, so that was our main motive. So this guideline only now being adopted for microzonation of entire Indian cities. Okay, so MOES doing the microzonation of 30 cities, they try to adopt this procedure which is become a part of NDMA guideline and the MOES microzonation guideline. Here I can note that whatever map we produced, actually I am showing you as a only the image file, even though we produced in ArcGIS, but it is not user friendly map as a macrozonation map of GEM. So GEM we have seen that I can zoom and then get the data, whatever grid point I am. Such kind of the user interface interaction map is not done for this study. Even though we have developed in GIS, somehow we couldn't develop those kind of website that OpenSeas or whatever is available nowadays. Maybe in the future some of the cities we can think of doing that kind of work which is more user friendly. I hope the IMD, okay, so also IMD, the MOES, okay, where they are doing the microzonation, they will prepare a map which is a user interface interaction map, what we have seen in the macrozonation of GEM model, global macrozonation map. Okay, so this is how the microzonation map or zonation map has to be developed for a particular location. So now we discussed a microzonation, macrozonation, how it has to be done with the example case study of world level, Indian level and Bangalore like city level. So let's see how the Indian seismic code, okay, is presenting a the zonation map of the country in the coming classes. Okay. So thank you very much for watching this video. So we'll see you in the next class. Thank you.